Hello everyone and welcome to another programming video. It's been a little while since the last one. I was a bit busy getting married, but now that that's all over with, we can get back into programming. And it's been a little while since I've looked at Do, and I kind of just bounced right off that project. I need to spend some time remembering how that works and trying to come up with a solution to the problem that I'm facing with it at the moment. So until then, I just had this idea rattling around in my head, and I really want to make a simple programming language that compiles to Java bytecode. Now, I use Java in my day-to-day, and it's actually a really fascinating topic, and I think it gets poo-pooed a lot, and it has its downsides, but it has a lot of advantages that I really like and that I really want to explore. Like, if you can write the front end to a compiler and compile it down to Java bytecode, you get an enormous boost with how much your language can do for not that much effort. So that's really what I wanted to do. And then I was thinking about what I want this language to be, and I haven't really decided, but I know it's going to have statements, expressions, loops, conditions, stuff like that. So we can get all of that stuff out of the way pretty quickly, and then we can start thinking about like features of the language and stuff like that, and we can just explore making a full end-to-end compiler. Well, not end-to-end, but like front end of a compiler. Yeah, sounds pretty good. And of course I'm going to be doing this in Java. Now this is probably a very interesting choice because I don't think a lot of compilers are written in Java. It's a garbage collected language, which makes it a bit unpredictable while it's compiling. But I don't really care about that. This is just a project to experiment with learning how to use Java bytecode and making a compiler. So I think it's fine. It's not supposed to be the next Kotlin or anything. And so I was thinking, what am I going to name this language? And I decided on Jura. So there's a convention in JVM languages to name them after islands. And I say convention because I think Kotlin is the only one that actually is named after an island. Java is named after the coffee that comes from the island of Java. So it's technically named after an island, but not directly. So I chose Jura because sorry for the flashbang, it's a Scottish island. It has a really short, simple name that's easy to say. Quite a lot of islands. I looked on the Wikipedia article of islands by population, and I had a look at the lesser populated ones just to see the more obscure ones, and they have a lot of names that don't really suit a programming language. But Jura, it starts with a J, which is already a plus, and it's 2 syllables. It's easy to say. I like it. So let's make a compiler. So how are we going to be compiling down to Java bytecode? So in my project, I have this library called OW2ASM, and what that does is it gives me an API to Java bytecode, which we'll get to when we get to the emitter. So if this is your first time in seeing how a programming language is made, I am probably not the best person for you to be learning from because I have never worked on compilers. I have never, worked for a company that makes compilers or anything. If you want a more sort of tutorialized introduction to making a compiler, I highly recommend a guy called Immo Landworth, who basically was the person who inspired me to start even dabbling in compilers. And he has a wonderful series where he makes a compiler in C# because he actually works at Microsoft, or he did at the time. I actually haven't checked on him in a long while. But he has a fantastic series making a language called Minsk, and it takes you through all of the steps, start to finish, for making a really, really good programming language. This is not that. This is not going to be that. What I do here is I just film myself programming, mistakes and all. I do a little bit of editing if it gets a bit slow, if I get bogged down by a problem. But for the most part, this is just watching me start to finish program something. Okay, so expectations set. Let's go. So how do we make a compiler? A compiler is a series of steps that transforms text into something a machine can understand. And so those steps typically are ulex, which takes the raw text. So just, let's say we have a program. See what I mean? Warts and all. I can barely type. And we say this is, 3 plus 4 times 5. This isn't a program, but this is usually how I start with making a programming language, is I make a simple expression evaluator first, because evaluating expressions is kind of at the core of most languages, especially the kind of languages that are like what we're going to be making here. And it really stress tests your parser, because when you parse this, you can't just parse it left to right naively. You have to understand precedence. So if you just did this left to right, you would get 3 plus 4 is 7, and then times 5 is 35? Yeah, God. It's 7:15 in the morning, so forgive me if my maths is a bit off. But that's not the right answer. If you were to type this into a programming language, if I said print 3 plus 4 times 5, not 45, but 5, you get, when Java wakes up, or when Gradle wakes up, Java, everyone. It's on over 1 billion devices. Gradle started in 16 seconds. Good stuff. Good stuff. You get 23. Why do you get 23? Because you do the 4 times 5 first, because multiplication has a higher precedence than addition, and then you add the 3. So you have to do something a bit more smart than just left to right. So I've kind of jumped around here. So lexing takes this string. This is just a sequence of characters, or a sequence of bytes, however you want to interpret it. And we need to turn that into a list of tokens, which are like the smallest unit of your language. So like in this Java program, package is 1 token, com is 1 token, the dot is a token, this public is a token, this class is a token, the word Jura is a token, and then this open bracket is a token. Notice that white space isn't a token. So we strip out the white space and we turn it into a list of stuff that we are, known entities. And then we take those and we parse them. And that's what I was saying. So if we were to lex this, we would have the token 3 plus 4 star and 5. And we need to take that list and kind of structure it into a tree. And so you want the tree to have this plus as the root. So if you imagine like in a tree in computer science, the plus is the root. One of the leaves, so it's a like a binary tree, it always has 2 children or 2 leaves. One leaf, or not leaf, but one child is a 3, and then the other child is the multiply, is the star. And the children of that root is a 4 and a 5. And so you'll end up, when you either interpret this program or you go to emit this program, you need to walk this tree. And so okay, I'm adding something. What am I adding? Look at the left-hand side. I got a 3, okay, produce a 3. Look at the right-hand side. Oh, I'm multiplying now. So we go into that. So I'll do a 4 times 5. That resolves, and then the root of that tree, or that like subtree, becomes 20. And then you have the 3 in the add, and then you evaluate that, and you get 23. Does that make sense? If that doesn't make sense, hopefully that will make more sense when we actually get to implement it. So that's parsing. Taking those tokens and turning it into a structure like a tree. Sometimes a language will have a step where it does type checking, which we definitely will be doing. So that takes that structured format and basically makes sure that it all makes sense. Like if I was to do this, you can parse this, and so you have a tree with plus and 3, and then a star, and then 4 and true. And as your type checker walks this tree, it'll see plus, and it will say, okay, well, this is an operation that takes integers. What do I have? Look to the left, I have an integer. Fantastic. I look to the right, oh, it's a star. Well, that's an operation that takes integers and produces an integer. Let's check. 4, that's an integer. True, that's a boolean. That's an error. And so we'll propagate that error, and we'll say, okay, well, the result of this is an error. And so 3 plus an error is an error. That makes sense? And so that kind of cuts out a lot of bugs that you would otherwise get at runtime if you weren't checking types. I don't know why languages don't check types. People say it's like, oh, it's easier to not think about types. The types are already there. Inside the computer are the types. Unless you're in B and everything is just a pointer length integer, there are types inside your computer. Either it thinks about it or you have to think about it. Sorry, bit of a sore spot. I fucking hate non-typed languages. What is that? 11 minutes in and I dropped a fuck? We're safe, as if I get monetized. So once you have that, there is another step, which we might not get onto today because it really only comes up when you're like optimizing or trying to compile things like conditions and loops, which is lowering. So you have these high-level structures. So parsing while making expressions also makes statements. The difference between the two, which we'll see as we get to them, is a expression will return a value, a statement does not. So you think of an expression in Java is, say, this string. That returns the value of the string. You could also have an expression which is, two strings plus. So this is a binary expression which returns another string. But this whole thing here is a statement. This doesn't return anything. I can't assign this whole thing to something. I can assign this to something, I think. No, I don't think I can because of the this. So this is even a statement. I don't know how Java parses this internally. Anyway, when you have conditions and loops, that's like a very high level statement, and there isn't really a, when you're compiling to, say, assembly or even Java bytecode, there isn't an if instruction. What you have are jumps and conditional jumps. And so what you have to do is you take your structured, statement in the AST, the abstract syntax tree format that we've got, and you basically need to rewrite it in something that is more translatable to your target. So what you do is you'll take, say, a conditional. So say you have like if some condition, some body, and that's it. You'll turn that into you'll evaluate the condition. If it is false, you jump over the body, and then you omit the body, and then that's it. And if you have an else, you have to then jump over the else. Stuff like that. And then when you go to omit, which is the next step, or at least it will be the next step that we have, you basically have a really friendly format to emit bytecode or assembly or whatever it is you're trying to do, because it's a bit more one-to-one. You have to kind of do this step anyway, even if it's not distinct, if you want to compile things like loops and conditions. And it's really useful if you have like very high-level structures in your language, right? If I wanted to have, say, pattern matching or lambdas or, stuff like that, that doesn't really map onto Java bytecode. Maybe lambdas do. I haven't actually checked. But if you're trying to parse to if you're trying to compile to like assembly, there definitely isn't anything like a lambda. I guess it's like a function pointer or something. But once you start adding higher level structures onto your language, the lowering step is where you basically desugar and you turn those into something that a machine can understand. Okay, I have been yapping for quite a while, and we have barely written any code. So, if you've made it this far, thank you, and let's get into making Jura. So the first thing we want to do is fix this, and we want to make our lexer. Let's make a lexing package because we're in Java, and we'll make a lexer. Well, before then, we need to define what our tokens actually are. So what I normally do, not token king. That was my nickname in high school. Token kind. So if we have a look at our example over here, let's get some room. We have 3 kinds of tokens. We have an int literal, so that will be our 3, our 4, and our 5. We have a plus, and we have a star. Those are our 3 kinds of tokens. What we also need is a token itself. So by itself, just knowing the kind isn't very useful, because tokens can have more information in them. Usually only like numbers. So like these are all int literals, but they all have obviously different values. So we need somewhere to store that. And then later on when we get to like identifiers, so you know, stuff like this main, this Jura, this word program, these are all identifiers, and they have some text component to them. And then also, you know, like a string literal or a Boolean literal will have a value, stuff like that. So we need a token, we need something that represents that token. So it will have a kind, and what I normally do is I just have the text stored in the token. And that's kind of it. And then we create getters for these. Maybe I'll add Lombok. I'm so used to having Lombok that now I don't have it. This feels horrible. But whatever. We have a token. So now our lexer, what does it do? Well, it just has a... let's see, how do we want to do this? We can either do it that we have a lexer that will just take in a string and return you a list of tokens, or we can have a lazy lexer. I say lazy because it's still going to load the whole thing in memory, but it's more like this sort of thing. And then, yeah. And then the lexer stores the program. I think this is okay for now. And then we want to know where we are currently in that program. And just to be complete, even though the compiler does this for us, manually set the cursor to 0. So when we lex, so you got to imagine our cursor is here. Well, it doesn't have to be. It could be here, or it could be here. So what do we need to do? First of all, if the cursor is greater than or equal to the program length, so say we got to here, or somehow we went past, we just return null. That'll be our signifier that we hit the end. I'm kind of thinking about whether Jura is going to have a null, because I really don't like null. It's a really weird concept when you think about it. Like, it makes sense in the context of like pointers, I guess, or like, you know, but it's a really I don't want to say dangerous. That makes it sound you know, way more than it is, but like it is kind of a dangerous concept. Like in Java, there is no way to know if any non-primitive type is going to just blow up your program if you do dot on it. So a lot of what I do at work is I'll have to do, like, there's a library we use, which is Apache, and you just say like not blank program, and then this basically just throws a more like descriptive error, and you can even have a message here, and it kind of has it at the point where it receives the value. So like, you know, if you imagine we passed null into lexer, we wouldn't know until we called lex. So yeah, I'm kind of thinking I'm going to do something about null in Jura. Like, you know, there is still null under the hood, but do you have access to it in the language? Maybe we say, I mean, this might be just yoinking stuff from Kotlin. I don't really know Kotlin or Groovy, but doing something like this means it's nullable. And yeah. Ooh, I've got Steam on. So yeah, ignore that. Someone playing Uma Musume. Anyway, so we're going to say, a long tangent is to say that null means we're at the end, or there is no token to be parsed. Stop lexing. The next thing is, actually the very first thing we need to do is to say, while the cursor is less than the program length, and the character we're currently looking at, so how do we want to do this? I guess program chart at cursor. So while we've got some white space and we aren't at the end of the program. So let's say we're here, and like let's say there's a bunch of white space, because you can do that. But this still compiles. We want to just jump to the next non-white space character, and it could be that like there's just a bunch of trailing white space at the end, so you want to jump until cursor is no longer less than the program length, and then this condition will catch that and return null. So while that, we just increase the cursor, so that's going to jump us to the next actual token we're interested in. Cool. Let's actually elect something. So now we know for certain we are just at the, or like we're just before, or I guess the cursor is at something we're interested in. So let's grab it. Program char at cursor, and let's switch on it. So what do we have? We have a plus. That's not a plus. That's a plus. So case that, I can never remember this new syntax. Is it that? We want to increase the cursor because we found a token. And we want to yield? No. Oh yeah, I remember. We want to return switch. And then we want to yield a new token. I love this new syntax. It makes it feel like it's not Java. So a new token, the token kind is a plus, and the text is this. We might want to automate this eventually. In fact, you know what we can do? We can, let me just say default yield. Is this the syntax? Just default null, yield null. Okay. I would have expected it to have told me that this is not necessary yet. It's too few case labels. Yeah. So instead of returning it straight away, we get a token, and we just cursor plus equals token get text length. There we go. Yeah, instead of yielding null, let's just, for now, throw a new illegal, doesn't matter. We don't want to be using exceptions in the real thing. You don't want your compiler to throw an exception if your program doesn't compile. You want it to report an error, and we'll get to that. Like if you watch Do, you know, that's the kind of thing we do. We don't throw an error when we hit a an illegal state. We just report a diagnostic and we keep compiling. But for now, we'll just say unexpected character, this fella. And we'll just format that with C. There we go. So now we know that token isn't null. Again, hate null. And then I think we can just do this. Is it like this? How do you do a switch statement in Java 24? Oh no, 21. I'm in 21. Different case kinds. Is that it? Welcome to Watch Sam Try and Do Java. I think that's it. And then we just return the token, and then it'll compile. Great. So now it's really easy to add a new case, because we can just It's just a single line. And you know, we can especially when we get to like multi-character ones, like if it's equals, then we check, oh, is there a less than afterwards? Well, that's less than or equals, which is a single token. But we don't have to worry about that yet. So we have those two. And then we want a case. No, we don't. This will be in our default. So if character is a digit C, we have a number. So let's just yield lex digit, and let's, do we pass in, yeah, we've already yoinked the first character. Although, no, doesn't matter. We'll do it like this. So we'll grab that one again, just because then this method feels a bit more standalone. I know it's a bit, you know, wasteful. We've already got the character, but I think it's, you know, it's not that expensive to grab a character out from the middle of a string in Java. This isn't Rust. And then we just say while the cursor is less than the program length, because we could have a number like here that goes away to the end while it's that, and character is digit C equals program. No, let's not get cute with it. Just is digit C. So while C is that, we want to at the end of this we want to increase the cursor so we don't stop. So that should sort that out. Is always true. I don't think it is. Okay, maybe it is and I'm being stupid. And we want a string builder digit new string builder, and we'll start it off with C. Why is that bad? Oh, because that calls that. Yeah, that's something I don't like, is that characters are technically integers. I'm thinking we might have more interesting primitives, but obviously they're going to map to the JVM primitives. But we'll see how well that pans out when we get there. Like, I think it would be nice to have like signed primitive or like unsigned primitives, but I don't know if the JVM actually supports those. But we'll see. So yeah, we'll not do that. So while it's a digit, digit append C. I think that's it. I think this is just wrong. So we want to say return new token, and the kind is an int literal, and then the text is whatever we accumulated inside our string builder. So why does it think this is? Is it? Do I need to be a bit more explicit about where cursor is coming from? I don't understand why it thinks this is always true if I'm incrementing the cursor. Oh, hang on. Yeah, we want to do that. So actually we can get cute with it. Is that any more readable? Not really. But hey, it saves us a line. The compiler is still doing just as much work. And then we don't even need to initialize this. We just say char C. Cool. So we should have a Lexa. It's what? Half an hour into the video and we've already got a Lexa. Cool. I promise the rest shouldn't take this long. So if we go back into Jura, which is over here, let's bring this back over to the big screen. We have lexing. So let's say Lexa equals a new Lexa, and we pass it in our program, which is going to have all this horrible white space just to test it. And then let's just say token while, let's just do lex, while token is not null, s out token get kind. In fact, let's just do something like this. Why not? And then we'll format it with token kind and the token text. And then we need to do that. It would be nice if the Lexer implemented iterator. Iterable or iterator? I think iterator of token. Has next and next. Yes, that's the one. So we'll probably need private token next. So has next, return next does not equal null. Next token n equals next, next equals lex, return n. That's probably a mighty scuffed way of doing it. And then we'll just say this next equals lex. That does kind of ruin what... no, what am I doing? What am I doing? I don't have to do that at all. I just say return cursor is less than program length. But then that's not true because it could just be white space at the end. I'm going down a bit of a rabbit hole here. Let's forget that. But that's, you know, that's something that we should probably do, is make these an iterator, so then we can eventually move to something a bit more lazy. Because if you have a massive file, you probably don't want to load that whole thing into memory just to lex and parse it. So yeah, you could you can sort of open up a file for, you know, emitting bytecode, and you just kind of have this chain that goes from the text lazily into the bytecode. Although then that kind of means it's sort of like a one-pass compiler. We'll get to that. Anyway, why does it hate this? Redundant called formatted. Oh, I didn't know you could do that. Cool. Learning new things every day from Java. What do we get? First try. First try. So look, we have a 3, a plus, a 4, a star, and a 5, even though we have all this crunchy white space in all these places. How about that? Let's do some parsing. So parsing, like I said, we need to understand precedence, and for that, we need to understand what kind of expressions we have. So what I'm going to do is I'm going to create a abstract class which is an expression, and that is going to have a expression kind, much like we had token kind. So what kind of expressions do we actually have in our program? We have an integer expression, so this is an expression that returns an integer. And we have a binary expression, so we have this, well, we have this binary expression, which evaluates to a single integer. So you imagine this is a single unit, like this. And now we have this binary expression, where on one side we have an int expression, and on the other side we have a binary expression. So this is why, like, it's a tree, you know, we have like a recursive structure. So the expression we are going to, how are we going to do this? Let's just say you have to, what's the easiest way to do this? Let's say it has an expression kind field along with a, how do I do this? There we go. A constructor and a getter. So you get all this for free. And so the two expression kinds we have are int. Let's not do int. Oh, that's my alarm. Sorry if you're also an Android user and that just triggered you. So we have an int. We'll just call it literal. Again, and we have a binary. So those are our expressions. So if we make a new expression, let's say we have int expression. Sure. And that extends expression. We'll create a constructor. Yeah, this is going to get annoying because we don't want to keep passing in the kind. We just want to say token kind in literal. Not token kind, sorry, expression kind. Is that a good way to do it? No, I don't like that. Instead of that, screw all that. We just have public abstract expression kind get kind. And then our int expression will just I'm so used to using a Mac. Now that I'm actually coding on Windows, I'm typing everything wrong. That feels nicer, I think. And then the int expression, we want it to take in its value, like so. And then we want a getter for that value. Whatever. There we go. Cool. That's our int expression. And we also have a binary expression. Like so. So what does this have? Well, it has a private final expression. So now we've got our recursion, left-hand side, and a right-hand side. And it also has a binary op, which we need to create. So if we make a binary op enum, we can do something very interesting. So if we say, what do we have? We have add, and we have a mul. But we can associate, you know, a precedence with this. So we can say that mul has a precedence of 2, and add has a precedence of 1. No, let's not do it like that. Let's not do it like that. Because you need to be able to know the precedence on the token. So we'll probably do that in the parser. Those are our 2 binary ops. So now we have all this. We can add constructor parameters for all of these. And how do I generate? I can never remember. Alt and insert. Unfortunately, I don't have those buttons on my keyboard because my keyboard is a Mac keyboard. Getters. There we go. Again, I wish I had Lombok. Okay. So how do we parse? Probably much the same way that we lex. So if we had a private final list of token, like so, we could make it an iterable of tokens. Pretty sure a list is an iterable. The sequence collection, extends iterable. So it doesn't have to be a list. So we could eventually be lazy. This might bite me in the arse. Let's see how this does. So we have some tokens. Let's expression parse. Eventually we're going to have statements, but we're not going to worry about that now. So we're going to parse the next one. So if tokens is it has next. Oh, we want an iterator. An iterator of tokens. If it doesn't have a next, turn null. Maybe I'm getting too cute with this. Maybe I should just use like a list and a cursor. I think this is fine. If we don't have a next, return null. So what we want to do is we want to return parse binary expression, and we want to pass a 0. And I'll tell you why. This is the parent precedence. So as we are recursively calling this function, we're going to pass in what our current precedence is. So we can say if we find something that has a lower precedence, we don't include it in our current expression. And so hopefully that will become apparent. So the first thing we need to do is we need our left-hand side. So let's say expression LHS equals parse primary expression. So these are our expressions that aren't binary expressions, basically, of which we only have one. So let's first of all token equals tokens next, and we know we have a token because we checked. This might get a bit weird eventually. So we want to switch on the token kind, and let's say expression. No, let's not worry about that. Let's just return. And if it is an int literal, we return a new int expression with integer parse int token text. And there we go. Anything else, throw new illegal state, unexpected token, blah. Like that. So we'll end up with more primary expressions, you know, like Boolean literals, string literals, variable assignments, array indexing, stuff like that. Stuff that you can imagine is part of a binary expression. But for now we only have the one, so it's going to complain at me profusely. So we get that. And then we want to say while. Do I want to say while? I want to do if not token says next. So if we just parsed and we got to the end, just return the LHS. Otherwise, token op equals tokens next. And we want to say int precedence equals op get binary precedence op. So we now have a token. It might not be a binary operator, but this is why I wanted to do the precedence checking in here, because we need to check the token. So we want to return switch. In fact, let's just take the token kind. We don't need to pass the whole entire token into here. And then we'll just switch on the kind. So the default will return 0. All tokens, unless I specify, have a precedence of 0. And so, as you can see, we pass in 0 here. So what we're going to do is we say if the precedence is less than or equal to the parent precedence, just return the LHS. Cool. So if we have star, return 2. If we have a plus, return 1. So now star has a higher precedence. As we add more binary operators, we'll adjust these numbers. But for now, it's just important that star has a higher precedence than plus, and plus has a higher precedence than everything else. So then we need to say while, we could actually simplify this. We just return the LHS and we just say while precedence is less than the parent precedence and tokens is next, we say that the LHS equals no, we say that the expression RHS equals parse binary expression with this precedence. And we say that the LHS is a new binary expression with that LHS, the op. We need to. Yes, we need to actually parse that op. So we say binary op. So let's call this the op token. And we'll call this the op equals, and then we say parse binary op, and we pass it the op token. So we get that, and we get the RHS. So we're going to do this continuously until, like, building up this tree as long as the precedence lets us. As soon as the precedence is less, we get out of there. And so we just have, let's just call that the token, return switch token kind, and then if it is, well, it's basically a kind of a mirror of this. So actually we don't need the whole ass token, we can just have the kind. Switch the kind, do this. Oh, I was like, why? You should be able to have this. If it's a star, that's a binary op mul. If it's a plus, that's a binary op add. If it's a default, that's a null, and we should never come into here. Cool. And we just pass in the kind. I think I've implemented that correctly. So I think this is called, this algorithm has a name, and I don't know if I've implemented it perfectly. But this should build a tree based on our expression here. But let's debug it before I just send it and run it to make sure it's actually doing what I want it to do. Because we could end up, well, we might not end up in an infinite loop because we are taking from the iterator. So this takes an iterator of tokens. So actually we want to probably build up a list of tokens is new array list, and we just want to say token while token equals lex. So we want to do the assignment while that does not equal null. Instead of just printing it, we just say tokens add token. There's probably a much better way. Like if this was actually an iterator, we could just like yoink that into a list, or we wouldn't even have to do this. But cool. So we just say parse. Yeah, this would be nice if this was an iterator as well, because now we're just going to do the same song and dance. While expression does not equal null. We only have one expression at the moment anyway, so actually let's just s out that expression kind. Send it. So we come into here. We've called parse. We have next. Parsing the binary expression with a precedence of 0. Great. So parse the primary expression. We get the next token, which is an int literal. So we return an int expression. Cool. We have a next, so we get the next. So the op token is a plus. We get the precedence of it, which is 1. And that precedence is, first mistake, the condition's the wrong way around. While the precedence is greater than or equal to that. Cool. Glad we checked. Otherwise, we wouldn't have got anything. So we get the precedence. It is greater than or equal our parent precedence. So the op is an add. And so the RHS, we now go and parse another binary expression, but with our current precedence. So we come in. Primary expression. LHS is the 4. So remember, we're now here. We're parsing this binary expression. We have a next. We get the op, which is a star. precedence is 2. Precedence is greater than or equal to our parent precedence, so this has a higher precedence. So now that we have this 4, we want to bind it to the following expression in the binary expression because it has a higher precedence than the one we were already parsing. It's a mul, the RHS, well, we've got to parse binary expression again. So we come in, LHS is the 5, we don't have any more tokens. So we return. So the RHS is 5. So now we can finally assign back to LHS a new binary expression of 4 times 5. And now we don't have any more tokens, so this is false. We return the LHS. So we go back to that original call where our LHS was 3. And now we've got our RHS, which is a binary expression of 4 and 5. And so we assign that back to the LHS, and then we've run out of tokens. And so our LHS is a binary expression. So do you remember I was saying our root is going to be the add. Our root is the add. Our left is 3. Our right is mul. And then the children of the mul are 4 and 5. So we have parsed that correctly. How about that? Again, first try. Well, let's not get too hasty. Let's see what happens. Let's just clean this up because we know that works. Well, not quite that much. So what happens if I swap this around? Does that still work? So what we should get is this plus is the root. Our LHS will be the binary expression 3 times 4, and our RHS will be 5. So let's not... Yeah, okay, we've got rid of the breakpoint. Let's just skip straight to here. So our expression, mul, is the root. Well, that's not right. Why do we have mul where the LHS is a mul of 3 times 4 and the RHS is 5? What did I mess up? I think I need to do this inside the loop. I think I need to do something like this, which is a little icky. Still hasn't worked, has it? And that just made that even worse. Okay, I'm going to take a break. I've been recording for nearly an hour now. I need some water, and I've done something very wrong. So I'll figure out what that is, and I'll come back. Okay, I don't quite know what I've done. I've looked at other examples of this, which is the recursive descent. I remembered the name of what this algorithm is. And I don't see any problems, and like this feels like this is the correct algorithm, but it isn't parsing it right. But let's just move on. Doesn't quite matter for what we're trying to do, because now we get to go on to the interesting stuff. So we've done lexing and we've kind of done parsing. I'm going to skip type checking for now. That's going to be its own video. And I'm going to skip lowering for now, because like I said, this only really becomes important when you get into higher level structures, or like higher level language features, like loops. Loops aren't a bytecode feature. So when we get to like loops and conditions, that'll be the topic of that video. So you've got all that to look forward to. So let's get to emitting. So this is quite interesting. I'm going to need to remember how to use the OW2 ASM library. So for now, let's just have an iterator of expression. Down the line, this is not at all how we're going to do it. So, like I said, we also need to have statements, but we're not bothering with statements now. We're just compiling a single expression. So, we'll just call that expressions, expressios. We need a constructor for that. And we're probably not going to bother with accepting any arguments about what we're compiling yet. So eventually we'll probably want to say like the name of this class. Yeah. Let's do that. So we want to have a public void emit. And this is just going to like one-shot emit the entire program. Sure. So give me a moment. I'm going to pull up my notes because I need to remember how to use this library, and then we will get to emitting. Okay, I have an old compiler I wrote, so this may not be the best way to do it, but what we want is a class writer. We want to initialize that here. We want to pass in, I think, compute frames for now, because I don't really want to think about stack frames yet. And then we want to emit. So we need a main method. So the way this is going to work, if I just yoink this. So like I said, you're kind of building up the... Why are there so many of these? You're building up the program in the API of this, which I really like. This I like less. I wish this was not strings, but here we are. So now we have a main method. So if I void emit method visitor mb and an expression. Well, what we can do is we can say for expression in expressions. Ah, you're not the one that allows me to do that. Annoying. How do I make you into an iterable? If I just do this, yeah, we'll figure out the conversion later. So for expression in expressions, we just want to emit with the main method visitor that expression. So how do we emit an expression? Well, we switch on it. Switch the expression kind. So we have two kinds of expressions. We have an int literal and a binary. And this would be a really good opportunity to use records, or not records, but like sealed interfaces, because then we would be able to do this next step for free. But I don't think it's really that important, because we're going to change all this, because we're not going to be emitting expressions eventually. So we just have an expression, because eventually we want to be emitting like lowered statements and lowered expressions and stuff like that, or like typed statements and typed expressions. But for now, we'll just cast that, and now we want to what is the syntax? Oh yeah, we want to visit an int instruction, and the instruction we want to do is an si push, assigned integer push, and we push the value in our expression. So if you're not familiar with Java bytecode, it's a stack-based machine. So what we're going to do is we're going to push the integer onto the top of the stack. And this is going to become more apparent when we get to the binary expression. So what do we do with a binary expression if we see one of those? Well, let's just cast it. Yeah, I think a sealed class is going to be the way to go, because then we can just switch on the class and we get the subclass for free. We get the binary expression, and then, why does it hit this? Oh, because I forgot the equals. And then, so it's stack based, right? So what we need to do is we need to emit, with the same method visitor, the left-hand side. We need to emit the right-hand side on top, and then, only then, we switch on the binary expression op, and then we don't have to have this. So if it's an add, we visit instruction sadd. What is it? Is it sadd? Si-add? Is it just add? Ah, I-add. So we visit the instruction integer add, and that doesn't take any arguments, because it knows that the arguments are the top two elements on the stack, and the same for mul. So we visit the instruction imul. That's it. Cool. So once we've finished emitting, we've kind of built up in memory the class, but we now need to actually create the class. So first thing we've got to do is we visit the return instruction. Is it ret or return? Apparently it's return. I don't know what the difference is. Then we need to visit the maxes. So this is basically, yeah, how big does the stack get and how big do the locals get? It can't compute the frames and the maxes as far as I know. I might need to look into this, but for now, we don't care. Just make it big enough that our program will fit. To do compute these properly. So we've done that. We want to visit the end of the method. So we've done all that. And then I am just going to steal how I did it before. So, right. Let's just say this throws. We don't care about the return for now. And let's just call this main class to match the... I guess it doesn't have to match anything. Yeah. So by itself, this isn't going to do anything because we've just emitted the expression. We're not doing anything with the expression. So I think we should print the result of the expression. So the way we do that, if I, again, yoink from my old compiler. Yes. So what we want to do is we want to push onto the stack well, let me just yoink this. So we want to visit the field out of system. So you know when we print, we want to get the field out of system. We want to put the value onto the stack, and we want to invoke the function println on that value. So this looks a bit gnarly, but basically, if you imagine this stack ways, we push system out onto the stack. Imagine this is the stack. On top of that, we push our value, and then we visit a function println, which takes in an integer and returns nothing. But it's a virtual function, so it needs its where it lives. So it takes both of these off the stack. That's basically what that's doing. Cool. Let's see if it works. So we have an expression, and I've reverted it back to the one that actually works. So we have the expression add left-hand side 3, right-hand side mul 4 and 5. So when we run this, we should see it print 23. So, well, first of all, we have to actually emit it. So let's make an emitter, bytecode emitter, a new bytecode emitter, and this needs to take an iterable of expressions. If I just do a list of the expression, cool, that is actually iterable. Nice. And then we just emit, and this throws because it deals with I/O. Let's just make the whole thing throw, and then if we run it, we got a main class that didn't seem to work. I think I know why. Why one related problem? Catch up. If we go back to the emitter, I think I missed a step. I think I very much missed a step. Yeah. I never visited the class writer. I didn't tell it what version we're using or anything. Yeah, this is what I was thinking of. So the output, we need to make it main. Let's not use version 11. We're not animals. Let's use version 21 for now. Let's try that again. There we go. And look, we have system print out, or system out print line 3 plus 4 times 5, which is exactly what we had here. Let's run it. I don't know if I can just run this. Yeah. Yeah, it doesn't quite know what to do with it. But we can invoke it with the command line. If I remember how. Give me a second. I think I can just run Java the file. Yeah. If I just do Java main 23, just like that, and so I can just change this to 6. Run the compiler. Back to the terminal. 27. 4 times 6 is 24 plus 3, 27. Cool. That's all cool, but let's add one more expression, and we will call it quits there. So let's add a parenthesized expression. So what if we wanted to add 3 and 4 first before we times it by 6? So we would get 36 instead. If I run this now, it's going to complain bitterly that unexpected character, open bracket. So we need, let's get rid of the flashbang. So we need some new tokens, or new token kinds rather. So we need an open paren and a close paren. And the lexer, well, these are really easy to lex, aren't they? Because it's just this. Yeah, it would be nice if I didn't have to repeat the character in these. Maybe I can add a special method for that, but that's that. So now we don't have an unexpected character, but what we do have is an unexpected token in our parser. So in our primary expression, if we see an open paren, we need to parse a parenthesized expression. So let's add one of those. So first of all, we need to add the kind. Parenthesized, and we need to say what that actually is. A parenthesized expression extends expression is expression kind parenthesized. So what does this have? Well, it just kind of has a expression inside it that it contains. And then we can just say get expression. Cool. So if we have an open paren, we need to parse expression. like that. Parse a binary expression, because that is the root. Or do we want to just parse? Yeah, we do need to check that we aren't just like, we don't have a token at the end, but we can sort that out later. So we get an expression, and now we need to assert that we have a closing bracket. So let's have a function which is expect, it returns a token called expect next, and it takes a token kind. Let's call this expected. So first of all, if tokens does not have next, throw new legal state, expected blah, but got nothing. Then we just say tokens next. Let's call this actual. If actual get kind is not expected, throw new illegal state, and then it's expected this, but got this. We format that with expected, and we got the actual. But if it was what we expected, we just return actual. What is this? Insert not null. No, I don't think I will. So then we just say expect next token kind close paren, and we don't need to return it. Actually, for something we want to do later, I think we actually do want to return it. And the parenthesized expression actually needs to have the open paren and the close paren. And the reason is we want to eventually report diagnostics. And to report the diagnostics, it's very helpful to know where in your code the issue is. And so what you do is you have spans. If you've watched the Do series, you'll be familiar with spans. But basically, you have like some start offset in your program and some end, or like a length in your program. And the way you calculate that is, you need to know when an expression begins and where an expression ends. So if I just had that inner expression, all we would know about where this parenthesized expression is that inner. And it's just nicer if we know where the open paren is and the closed paren is, because it might not necessarily be on the same line, and all of that. So if we add those to the constructor, then we're good, but we don't need to actually return the parens for now. Eventually, like, I'll have something like this, which is like abstract, span get span, something like that, and then every expression needs to be able to tell me what its span is. We'll call this close paren. And then we just yield a new parenthesized expression where the open paren is that token at the start, the expression is the expression, and then we've just got the close paren. There we go. And let's actually add a little stop gap into our emitter. And we just say the default throw new illegal state unexpected expression this. So what we expect to see is that we should have unexpected expression parenthesized. Expected close paren but got nothing. Ooh, okay. Why is that? We parse the expression, parse the binary expression. So let's see what we actually get here. So what's our expression? 3 plus... Interesting. I think we went too far. I think we went too far. What tokens did we get? That's here. What tokens did we get? It'd be nice if these had to string 3 plus 4 star. So our Alexa was wrong. Ooh, I think our Alex digit goes too far. Digit append C, cursor plus plus. Ah, yes. I see. Because we advance the cursor again, we check. Oh, it's not a and then we advance it again by the length. So that actually didn't cause any problems before, because we always had white space or the end of file after the integer, but now we don't. So actually we can't advance the cursor inside. So let's just say int I equals cursor, and then while I is that, and then while the char at I, and then we just advance I. So we don't affect the global cursor, we just have a local cursor. Expected close parameter got nothing. What do you mean? Okay, what do we have now for our tokens? So we have open 3 plus 4 close star int. Okay, we Alex it correctly. So the parser, we get the expression. The expression is add mul 6. How strange. Is it because we're advancing here? Yes. We advance even if we return. So we need to kind of peek. Does this have a peek? Doesn't have a peek. Interesting. Very interesting. How do we solve this? I guess we don't make this an iterator. We set this to a list and have a cursor. I didn't want to do it like this, but I think we're gonna have to. So not if tokens has next, but if cursor less than or equal, no, greater than or equal tokens size. Same here. While cursor is less than token size, token equals tokens get cursor. Yep. And then if we aren't happy, or if we're happy with that, ooh, one moment. Okay. So we get this. If we aren't happy, we return. Otherwise, we have the op token. We just advance the cursor here. Okay. Why is this unhappy? Because this is always true. If you return the LHS, I think we have to advance the cursor here as well. I don't know. Let's see what it's chatting. We can just pass the tokens. So parser, let's go into here. Quite right. token equals tokens get cursor. Look, if there are errors, why is this not got a squiggly? For God's sake. If cursor greater than or equal to greater than or equal to token size, and then tokens get cursor. Any more? No? Cool. Aha. This. Tokens get cursor plus plus. So primary expression, we get that. The token is open paren. We step in, parse binary expression, parse primary. Token is a 3. Okay. Expected close paren but got int literal. Okay, we're not advancing it somewhere else. So parse the expression, parse binary expression. Okay, I've been going for a little while now. I promise. Well, I just wanted to add parenthesized expressions, but it's kind of just exposed a bug in my compiler. This is why I said, if you want a proper tutorial on how to make a compiler, this isn't it. This is just, I hope this is entertaining, or at least interesting, and you're watching it because of it. But, God. Okay, so the cursor is 3. We come in here. The op token is a 4. So the precedence is 0, so we return the LHS, which is a 3. That's not quite right either. Okay, I think because we don't actually need to advance after we get the primary expression. There we go. Okay. Yeah, I want a more sophisticated system for advancing the cursor or getting the next. I think having a peekable iterator is probably the way forward. Anyway. Okay. So now we're here. So if we have a parenthesized expression, first of all we want to cast. All we really want to do is just emit the inner expression. Like that. Because, you know, we've already sorted out the precedence. Now we're just dealing with a stack machine, so there doesn't need to be any kind of like parentheses in our stack machine. So that compiled. So as a reminder, we want to do this operation first and get 7, and then we want to multiply it by 6, which is 42, I believe. But that doesn't seem to be what we've got, does it? I think our precedence is not our precedence, but our parser is just a little bit balked. If I do it this way around, is it happy? Yeah, and look, the decompiler. So what we're looking at here is a decompilation of the bytecode. So I wonder, can I? There should be an option somewhere where it will show me the raw bytecode. I can't remember where that option is. It's very adamant that it wants to show me the decompiled. But this isn't what we emitted. We emitted raw bytecode, and this has so this thing Fernflower looks at that bytecode and turns it back into Java. And as you can see, it has in fact put 3 and 4 in parentheses, because it's interpreted the order in which we do the operations to be like that. So if I run it, we get 42. How about that? I wonder, can I chain these? So what? Hang on. Let me pop up the calculator. So 3 and 4 and 5 is 12 times by 6, 72. So we should see 72. It failed. Did it close paren but got plus? Okay, our parser is absolutely fucked. I'm gonna fix that off screen and maybe do like a little addendum to this, or maybe at the beginning of the next episode. Bit of an unceremonious end, but like we've got somewhere, right? We can compile simple expressions if the precedence doesn't get too wonky. We lex it. We have a very easy way to add new tokens, and we could probably do an easier way if we make a little helper method for single character tokens. And we have a system for emitting Java bytecode. Admittedly, this is all going to change once we actually do type checking, lowering, and we add statements. Because really, we don't want to be like going through expressions. We want to be going through statements, and statements contain expressions. Right. Because like we've kind of like bodged it into a statement by wrapping it in a print, which is good for debugging, but obviously, you know, for an actual compiler, you don't want it to print every expression that you've done. So I think that's it for today. This has been quite fun, actually. As much as this has like been chaotic, that's kind of what this channel's all about, is just chaotic programming. Like this isn't tutorial. This is you're just watching somebody program. And if that interests you, thank you for coming along with me and getting this far through the video. If you are this far, let me know in the comments, like, what do you want this language to be like? Like, I'm thinking it's going to be like JVM adjacent, like kind of Kotlin-y, kind of groovy-y, Java-y. But obviously it's not going to be like a production language. It's not going to be as fancy as those. I want it to be Turing complete, which, you know, is a very low bar. I want it to be Turing complete. I want it to be compiling to JVM, which means we might be able to do some interop, but we'll see. But using that, we might be able to pull in some libraries for Java, and we might be able to do some like graphics programming in it, which I think would be really interesting. You know, trying to write something that will put something on the screen. I know there's like a raylib implementation in Java, not implementation, but, you know, like binding in Java. So if we can get to that point and do like a raylib speedrun in Jura, that would be very cool. But yeah, if you have any suggestions or like any like how you want this language to look, let me know. And if you absolutely fucking hated this video and somehow made it this far, good on you. But let me know. I don't know what I'm doing. I just have an idea and I'm like, I want to share this with the world. I'm just going to record myself programming it. And if you don't like that and you have a constructive criticism, let me know. Otherwise, maybe I'm just not for you. But anyway, all that's to say is thank you very much for watching. Next time, we're going to probably extend this to have statements. And that way we can have multiple expressions and we can print multiple things. We're going to add maybe some basic type checking if we add some more types, but maybe not. Maybe we're just going to flesh out what we have and fill out the whole gamut of like binary expressions we can have with numbers, stuff like that. Yeah. Cool. I'll see you there. Thanks for watching. Bye-bye. Okay, small addendum. I figured out what was wrong with the parser. So it was really stupid. This while, it was an if, and that is why this was complaining. I should have listened to the compiler complaining. Sorry. Of course, this is always true because it only ever runs once. It needs to be a while. We keep parsing until either we hit the end of the tokens or our precedence no longer holds. So that's what the problem was. I don't know why this was an if. I must have just not been thinking. And then this exposed another problem, which is if we call expect next and we actually get the token, we want to advance the cursor because this isn't advancing the cursor. And I think it makes more sense that the expect next function advance the cursor rather than having to do it manually every time we, call it. So with all that, this so this is what we had before. We had 3 plus 4 times 5. Okay, so the precedence should bind the 4 and the 5 together to get 20, and then it should print 23. If we instead wanted to do the 3 and the 4 first times it by 5. So this didn't work before because we had the if, so it was only parsing the first one. Now it's a while. It'll keep parsing until it no longer makes sense. So if we do this, it should add 3 and 4 together to get 7, times it by 5 to get 35. Fantastic. Cool. And then we could add another 5 onto there. Why not? And that should be 40. There we go. So now we have a working lexer, and parser, and emitter. So great. That tidily wraps up the video. Anyway, thank you very much for watching, and I hope to see you in the next one. All right, bye-bye.